Alrighty, so we are on section 2, part 5 for biology, enzymes, as per usual, and I'm gonna say this at the beginning of each one. You need to be writing down each of the bullet points from the syllabus and then doing the notes underneath. The lovely thing about biology is whenever it says define, that is the answer. There's no real need to do anything else. So let's talk about what a catalyst is. Define the term catalyst as a substance that speeds up a chemical reaction and is not changed by the reaction. So what that means is, let's say you have a chemical reaction. So a chemical reaction is A plus B turns into AB. So normally what we can do to make this reaction happen faster is we can increase the temperature so that the A and B are moving faster so it happens quicker. But another thing that we can add is something called a catalyst. And what the catalyst does is it somehow makes this reaction happen faster. For the most part, what it actually does is it just provides a place. So, the chill out spot. And now that the chill out spot is there, both these guys will come chill out and then they'll react. So in school, the way to think of a catalyst, it's the instigator. I don't know how to spell instigator. You know, the person that starts the fight that says, oh no, he didn't, and no, you won't. And then the two people fight, A and B fight, and then because, the person in the middle is saying a whole bunch of dumbness to A and to B, A and B fight and get suspended while this person, the catalyst or the instigator, doesn't get in any trouble at all. Didn't throw any punches, just went around talking trash. So that's what a catalyst is. It's someone that speeds up a reaction. It's a substance that speeds up a reaction. Now in biology, we make the substances needed to speed up these reactions, and we call these substances enzymes. So a few rules that I have for enzymes to remember. Enzymes build things, enzymes break things. They are proteins, which means that they have to follow all the rules of proteins. They can be digested. And they're special, meaning that one enzyme does one job and another enzyme does another job. Enzyme A does not do the job of enzyme C. Okay? So these are pretty basic, but they're four kind of simple rules about enzymes. Now, this is kind of how enzymes work. So what you have is a shape. Okay? So there's our enzyme, and it's a female enzyme, I guess. Alright? And you'll notice that at this point, it has two spaces for something to land. Okay? Now the spaces are very specific, and we call this point where the two shapes are the active site. It's the part where all the action happens. So the only thing that can land on this is a triangle shape and, an oval shape. Alright? So this is an enzyme that builds things. Actually, it could be either. So my substrate is just floating around. Okay? Nothing special. All of them are just, floating around, floating around, floating around. All of them are doing that. I can't move them all at the same time, people. And what happens is, when my substrate lands on my enzyme correctly, something happens. So while the substrate's floating around and floating around, one lands like this, and the other one lands like that. And when they land correctly, my enzyme does its job. It doesn't actually do a job, but it's that meeting place. When it lands correctly, the reaction happens. And in this reaction, they suddenly join together and they float away as that. Okay? So that's an enzyme that builds things. The same situation could be for one that breaks things apart. Let's say you have your substrate, and your substrate is shaped like this. Alright? And when it lands in that spot, it's going to fit perfectly, and then it's going to break it apart and break it into, undo that, two separate shapes. Enzymes build things up, enzymes break things down. Okay? So this is just a theory. No one's actually sure if this works or if this is how it goes, and it's called the lock and key theory. Okay, lock and key theory, or lock and key model, whichever one you want to call it. So that's your lock and key. Lock and key is all about active site and the fact that only specific substrates, those things, can fit on the active site. Moving on. Enzymes are proteins, which means they respond like proteins. So think about eggs, proteins. If the enzyme is in an environment that's too hot, it gets destroyed. Okay? And just like all kinetic theory, as the temperature increases, because the molecules are moving faster and more molecules can land on that active site, right? If the molecules are moving around faster, there's more of a chance that they'll land in this correctly. So, as the temperature goes up, the activity goes up. But what you notice is that around 37 degrees, the activity suddenly drops. Okay? And the reason why is because at 37, depending on the enzyme, that active site, which was very specific, when it gets too hot, it starts to break down. It cooks, just like your eggs. Alright, and when it cooks, it can no longer do its job. So when the temperature gets too high, your enzyme's active site breaks down, and we call this process, the enzyme becomes denatured. When it's denatured, it's not dead because it wasn't alive to begin with, but it can no longer do its job, so the activity plummets. Now, the exact same thing happens with pH. So same graph, but that was a genius move. That didn't help at all. Same graph, but with pH, which measures acidity. And in my opinion, it's the exact same graph, but some argue that I've noticed that the GCSE likes to mess with you, and they'll make it more like this. I should have hit where there's no steady increase, like in temperature. The enzyme isn't dead at 0 degrees, it's just cold, versus at extreme acidity. Yeah, that works. At extreme acidity, it just doesn't function at all. And then you'll notice for temperature, it drops off suddenly. So the red one is temp, and that's going to be 37. I probably shouldn't put this on the same graphs so you don't get confused, but hey. And for the black one, that's pH, and that's going to be a pH of 7, which is neutral. Alright? And the exact same thing happens. If you were to pour acid on your steak, what do you think would happen? Boop. Denaturation. Alright? So enzymes denature at extreme pHs. Some have been developed to work best at extreme pHs. For example, there's an enzyme in your stomach that likes to be in acid, which makes sense because your stomach is full of acid. And if someone can figure out why our enzymes work best at 37, it's because that's body temperature. Enzymes work best when you're regular temperature. If you get too hot, they stop working and you pass out. Alright, let's see what's next. So, just for clarification, the reason why enzymatic activity, I just made that up and it works, increases as the temperature increases is because the substrates move faster. Increasing kinetic energy is the term they want you to use. You already know that. Molecules always move. They're always moving. But if you increase the temperature, they'll move faster. If they're moving faster, there's a better chance that they'll fall into this spot. Think about trying to shake sand out of a sifter. Only certain pieces of sand could fit through the sifter. You shake the sifter slow, only a little bit will fall. You shake it fast, more will go through. Same idea. Part 2, after a certain temperature, enzyme becomes denatured, active site destroyed, can't do its job. pH is the exact same idea. At extreme pHs, active site is destroyed. Please note that once the active site is destroyed, it's done. So if you have something in an acidic environment and then turn it to neutral, you actually won't get any reaction because they'll all be denatured anyway. Versus cold and hot. Well, hot's the same idea. Okay, let's see how quickly I can do this. Inside of a seed, there is... The reason why we can eat seeds is because it has stuff in it that we can use, right? So there's starch and fat. And inside of the seed also are enzymes that are sleeping. They're dry. And so when the enzymes get wet and warm and they get a bit of oxygen, what they do is they activate and they turn the starch into maltose. I wonder if I should tell you the name of that enzyme. Nah. And they turn the fat into fatty acids and glycerol. Well, they don't turn, but they catalyze. Okay? Yeah, I'll tell you the name of the enzymes. So inside of the seed, you have amylase, which attacks, which goes for the starch, and you have lipase, which breaks down the fat. All right, well, not breaks down, but for soaps, same idea. If we use washing soaps that have enzymes in them, at certain temperatures, in the right conditions, they will attack, or not attack, but they will break down biological stains, armpits, pee, things like that that are caused by the body. They will break down the stains and get rid of it. So the conditions needed are alkaline and low temp. If you put hot water in the washing machine that's hotter than 37 degrees and you use the expensive Tide that has the enzymes in it, you just wasted your money because you'll denature the enzymes and you'll never get the stain out. The last one, for making soda and juices, remember the cell wall is around every cell in a plant, and the cell wall is very tough and very hard. So in order to help make juice, what we do is we add pectinase. And what the pectinase does is it breaks down the cell wall of fruits, specifically apple, and releases the juices. I thought I picked brown, so that you can get some lovely apple juice. Okay. Someone needs to remind me on Edmodo to do the penicillin lesson, because I'm gonna skip it. Alright, so let's go back and check what we've covered. Define the term catalyst, bang. Define enzyme, bang. Investigate and describe the effect of changes in temperature and pH on enzymatic activity, done. Explain lock and key, done. Explain the effect of changes in temperature and pH on enzyme activity. Please note there's a difference between these two. One says investigate and describe, and one says explain. So in this one, you just have to draw the graph, and on this one, you have to say why the graph looks like it looks. Okay? Describe the role of enzymes in the germination of seeds. Germination means sprouting. Okay? When the seed's starting to go, or when it's starting to germinate, amylase is activated, lipase is activated because of the water, breaks down the starch, breaks down the fat. Outline the use of microorganisms, I skipped that, and enzymes for biological washing powder, done. Describe the role of fungus penicillium, so I skipped the penicillin stuff, okay? Someone needs to remind me that I skipped it, because I will not remember. And that's a wrap.